Okay, here we start again. Apparently these videos can only be 15 minutes long, so we'll learn as we go. So, back to William Herschel. So you can see there how he has thermometers and he was measuring the temperatures of the different colors of light. Well, something interesting that happened to him was he had a thermometer that was beyond the red color where we couldn't see any light at all, but the thermometer was sitting there and it registered a temperature. And he's like, what's going on there? There's no light there and it's getting hotter. So what's going on? Well, he realized, let me page down, okay. He realized that beyond the red color, in this area of color that we can't see with our eyes, there was another type of light invisible to human eyes, which we call infrared. Well, that was kind of interesting. We thought all the light was just the colors of the rainbow, and now we've discovered one that we are not able to see, but it's giving off heat, so it's really there. So John Ritter comes along, and he was doing experiments with chemicals. He had this silver chloride, and he noticed that it would change color with the higher energy lights. It would change color faster. So if he did a low energy light like red, it would change color slowly, but if you did a high energy light like blue, it would change color very quickly. Well, he exposed it to some light, and it started to change color without any evidence of some light that we could see. And he discovers that there's actually a light beyond the violet end. So down here is an ultraviolet light that there again we can't see with our eyes. It's there, it's even hotter than the blue light, but our eyes are not able to detect it. Now, light is an interesting thing because with things like sound, it requires, for sound to get from my voice to your ear, it requires air. So when I speak, it compresses the airwaves as it travels to your eardrum, makes your eardrum vibrate, and then it makes sound to you so you can hear. It requires air. So if I was speaking to you on the moon, where there's no air, I would sound like this. It would sound just like that. You couldn't hear me at all because there wouldn't be any air molecules to transmit that sound. So those are called mechanical waves. But light waves don't travel that way. Light waves have two parts to them. They have an electric field and a magnetic field, and they're perpendicular to each other and travel through a vacuum. So electricity can be like hair. You've had bad hair days like that before. And magnetism, you know what magnetism's like. So when you combine those two things together, there's our magnet with a magnetic field. When you combine those two things together, you get a light wave. And that's why we call it an electromagnetic field or electromagnetic radiation is light. So the magnetic field goes one direction, the electric field goes the other. They travel in waves with wavelengths according to what type of light they are or what color they are. So a changing magnetic field will induce a changing electric field, and vice versa. The two are linked. So once begun, electric and magnetic field changes could continue to trigger each other. So a magnetic field will make an electric field, and an electric field will make a magnetic field, so they can propagate and they can essentially go on forever. So there's another drawing of it. These fields are perpendicular to each other, and once formed, they travel at the speed of light until interaction with matter. Their waves can travel. I'm going to have to fix that slide. Solids and through solids and the vacuum of space. So there again is a little link there, which I'm not sure will work or not in this type of video, but you can give it a whirl there and see if that will pause it, and click on it and see if it does anything. So you can see, like with a jump rope, if you have more energy, you're going to make the rope go at a higher frequency than if you wiggle the rope slower, it's less energy. So it's sort of like that with light waves. And there again, there's another picture of how we kind of think of the photons traveling with different energies. All right, so this is interesting. So we have visible light with the colors of the rainbow right there in the middle of this graph. Those are the colors we see with our eyes. But there are many, many, many more forms of light that we can't see with our eyes. Gamma rays that are very energetic and go the other one direction all the way through to radio waves on the opposite direction that are long wavelengths of light with low energy. But remember again, they all travel at the same speed. So I like to liken it like you're going on a trip. You're starting at Los Angeles. You're in your car and you have this gigantic reel of ribbon. And you are going to unroll the ribbon as you drive down the freeway going to Seattle. So out your window, you're unrolling the ribbon all the way to Seattle. 1,500 to 2,000 miles, somewhere around there. Now you drive back halfway and you take out your pair of scissors and you clip out 1 inch of the entire ribbon, that you had unrolled all the way from Los Angeles to Seattle. 1 inch. That is how much light you see with your eyes. 1 inch worth. All the rest of the ribbon are types of light that we can't see. We can't see ultraviolet, X-ray, gamma, infrared, microwave, or radio waves. But they are there, and we have cameras that can detect them, but our eyes are not able to. So here's just kind of an illustration of the wavelengths. So remember, wavelength is between crest and crest. So with gamma rays, the wavelengths are so small, they're about the size of an atomic nucleus. An X-ray, a water molecule. You go up to visible light, just past visible light, and the wavelength would be about the size of a piece of bacteria. And you have needles, and then you have people, and radio waves can be really long, football fields long, or buildings long. So gamma rays are very, very energetic. They are dangerous to people. We wouldn't want any of those around. Some examples. Let's look at lightning. Lightning strikes, we can get some gamma rays. Nuclear explosions, we can get gamma rays. The Incredible Hulk, he was exposed to gamma rays and didn't turn out very pretty. So the next on our list would be X-rays. X-rays are also very energetic. That's what they shine through our bones, and the bones, when the X-rays come in contact with these tissues, well, I'll just read it. This beam travels through the air, comes in contact with our body tissues, and produces an image on a metal film. Soft tissues, such as skin and organs, cannot absorb the high-energy rays, and the beam passes through them, but dense materials inside our bodies, like bones, absorb the radiation. And that's how they can tell we've got a broken bone or not. So next on our list, we have ultraviolet light. And ultraviolet light is pretty energetic as well. We get most of that from the sun. So the sun creates 3 types of ultraviolet light: UVC, UVB, UVA. UVC gets absorbed by our gas layers and our outer ozone layer. And that's good, because that's not really good for us. UVB, a little bit gets through the clouds. UVA, most of it does get through the clouds. And the UVA is what sunburns your noses, why you put on the sunscreen that says UV protection. UV rays are harmful to life. So if you look at the little diagram to the right where we have some DNA and some chromosomes in there, when you have incoming ultraviolet light, it either damages or breaks the bonds in there. So it can either cause mutations, cancer, or even death. So UV rays are something we should protect ourselves from. Then we have visible light, what we see with our eyes, the colors of the rainbow. After that, we have infrared. So infrared is a longer wavelength. Infrared we can pick it up with temperature. We use it in our remote controls. When we shoot our TVs with it to change the channel, we don't see light go from our remote to the TV, but it's there. We just can't see it with our eyes, and that's what the TV can pick up and read. Infrared can distinguish on body temperature. We can use this in night vision goggles. Can pick up the heat of individuals. It shows you on the graph there that the brighter white, yellow light is hotter than the darker areas. And notice the guy's glasses, so the infrared is not going through his glasses there, so it's showing it dark. Healthy plants reflect more infrared radiation than an unhealthy plant. They can actually do studies of the health of forests by cameras overhead that take pictures of things on Earth to see how healthy the plants are. Now we have microwaves. You're pretty familiar with microwaves. So microwaves are a form of light. They come in and they cook our food. They actually rotate the water molecules that are inside our food, which causes friction, causes heat, and warms our food up. If you're worried about cell phone microwaves, stick a piece of popcorn in your ear. When it pops, it's time to hang up. Not true, but you could try it. Be interesting. You could report back if it pops in your ear. Radio. Now you've seen pictures probably in the movies of these great big dishes. These are pretty interesting. Now remember, radio waves are the low energy and they're really long. So to capture them, they have to have great big dishes like this. Now in New Mexico, you can go to visit these. There's about 27 of them that are all lined up together, and there's a visitor center, and it'd be a nice weekend trip if you're interested in this. It's kind of fun to go to. So the radio waves come into these dishes, and they are reflected up and then sent down by a signal to the computer. Now remember how we can add a couple of wavelengths together if we line up the crests and the troughs and make that signal stronger? That's what we do with these radio waves. They're very weak. And so to be able to really get a signal from space and radio, we need to add a bunch of them together, which is why there are so many of them in a row like that. They're all lined up perfectly, so the crests and the troughs of the signal are lined up, and we get a higher amplitude, and therefore can get pictures of things in space. Alright, so concept question. If gamma rays have higher energy than radio waves, which travels faster? Boom, 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 boom. They both travel at the same speed. Okay. Now this is a picture of the Earth's surface, and we have an atmosphere up there, and it's showing which types of light come through the atmosphere and can land on the ground. So fortunately, the gamma rays and the X-rays keep it from going through, or the atmosphere keeps those from going through because they would harm us. Visible light makes it through, just a little bit of ultraviolet. Infrared, just a little bit here and there. Microwaves, pretty much blocked. Radio waves make it to the surface, why we can have these great big antennas. So we are protected by our atmosphere in many ways.